This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Okay. All right. You guys, and who else? That's all. Okay. I haven't got very much housekeeping today, except don't forget assignment 1. I was going to say assignment 4. Assignment 1 is due today at 4 o'clock in the little letter box. Yes? I just put it online. It's online already. I did it on yesterday. Oh, is it? Did I drag the wrong? Oh, it shouldn't have let me have the same name. I'll check.
There's 2 there.
Yeah. Okay, you opened it up right? Okay. All right. So don't forget assignment 1 is due today at 4 o'clock in the little pigeonhole. Make sure you put it in there. I've released assignment 2 as well. That's due 2 weeks today. So make sure you get cracking on that one. Assignment 2, here's a little tip for you, is much more challenging than assignment 1 because I can ask you about more challenging things, all right? So don't leave it till the last minute. It's going to take a little bit more thought than the first one. Okay. The other thing I wanted to tell you is completely unrelated to this course, but you might be interested anyway. The library is getting rid of heaps of books, and they're just going through, starting at like call number 0 and working their way up to 900, and then they start again and they work their way up to 900 again. They get all the books that they're going to chuck out and they put them on some trolleys downstairs, and if they're not gone in 3 days, they get chucked in the bin. So if there's anything you want, you should go and have a look. So when you go in the front door of the library, they're kind of on the ground floor there and over in that direction. I think there's about 12 trolleys of books there today. Most of today, I think, is chemistry and some physics. Okay, but they also go through engineering and all sorts of stuff. So it might be worthwhile. There are all sorts of things. There are like research textbooks. There are like textbooks for class. There are books that are full of just questions related to this course and probably lots of your other courses as well. So it might be worth having a look at them. All right, does anybody else have any other housekeeping questions? Not today. 50 million questions on Monday and none today. Okay. All right. So we're talking about eigenvalues and eigenvectors, and we're going to keep talking about them for a while yet, but today we're going to actually start using them. Okay? And then next week on Monday and Wednesday, we're going to finish off eigenvalues and eigenvectors and how we're going to use them. So last week in this room, we started talking about eigenvalues and eigenvectors. And don't forget, I'm harping on about this. But don't forget, this is, you were looking for special directions of this, special directions, that's this one, of this matrix here, so that when you do this linear transformation, you get the same direction back, but maybe a different length. Okay? And by direction, the same direction, I mean it could be forwards or backwards, but still along that same line. Okay? So because it's a homogeneous system, we can find when the determinant of this coefficient here is equal to 0. That's going to tell us the lambdas. Stick the lambdas in here and we can find the x's. Okay, that's what we're doing. We did all of this stuff. Da 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 da. Here. Okay. This is what we're up to now. So we did that first little paragraph on Monday. Here's a little theorem. If you multiply all your eigenvalues together, the number you get is exactly the same as the determinant of the matrix. Okay, that's a handy thing to know. And I can prove that to you if you want me to, but you probably don't. And it's all to do with the fact that determinants are associative. But anyway. Okay, the second one here is probably the more useful one. If you get a trace of a square matrix, so the trace of a matrix is when you look at the diagonal, that main diagonal, and you add up those numbers. That number that you get from that is the same value as if you added up all the eigenvalues. Okay? Now this is a really handy one, and I'll tell you why. When you find your eigenvalues of a matrix, particularly a 3 by 3 or something bigger, you're doing like a fairly long calculation where it's easy to make a mistake, right? But you get these answers at the end for your lambdas. You can really check them really quickly just by adding them up and add up the numbers on the matrix that you started with and see if you get the same number. If you don't get the same number, then you probably made a mistake. Okay? So that second one is really handy and you should use that one when you're doing assignments and stuff. And the exam, it takes like 5-10 seconds. Okay, we're going to do an example of that one. This one. Okay. All right, find the determinant, the trace, and the product of the eigenvalues, for example, 43 and 45. So this is great because most of the hard work is done for us, all right? So 43, let's just write down what they were. So we found lambda 1 was 7. And we found lambda 2 was -3. Okay, so the question is getting us to find the determinant, the trace, the product, or actually we have to find the sum of the eigenvalues as well. All right, let's do the determinant first. That's going to be 3, take away 24, minus 21. Okay, and lo and behold, if we do lambda 1 times by lambda 2, we get the same number. Okay, so that's a little bit handy. It's a little bit handy because when you get to a 3 by 3, it's sometimes a bit of work to find the determinant. The other one's the most handy. Okay, the trace of A is going to be 3 plus 1, and lambda 1 plus lambda 2. Ta-da! Okay, so this one is really fast. You can check this one in the exam or in your assignment in like 10 seconds. Okay, so there should be no excuses for picking a wrong eigenvalue without checking that. All right, does anyone have any questions? That's pretty straightforward, right? Okay. Bless you. By the way, this little trick, or both of these tricks, also work for degenerate eigenvalues. So if you've got two eigenvalues that are the same, you just have to add it up twice. Like however many times it's repeated, you include it in the sum or the product. All right, you guys find the determinant. Shout out when you get the answer. Didn't give out any lollies on Monday. yes, it is. I am that clever. I can manage that one. Did anybody get there yet? Plus, minus. Plus, minus. Nobody said it over there. Who said it over there? Nobody who wants a lolly. Who said 12? Yeah, you can have a lolly. All right, so this gives us 20 minus 8 is 12. Oh, I lost it. Here you go. All right. So then if we do lambda 1 times lambda 2 times lambda 3, 4 times 3 times 1 is 12. The trace of the matrix, remember the trace is just the sum of the elements on that main diagonal. So this is the useful one because it's really fast. 3 plus 0 plus 5 is 8. Here we go. All right, so that's a super handy trick to have up your sleeve. Does anyone want to ask any questions about that one? No? Pretty straightforward. Okay. Hold on. Oops, that's not what I want. Ah. Maybe I'm not clever enough to drive this thing. Okay. All right, diagonalisation of a square matrix. All right, here's the other one thing I can tell you about what you can use this stuff for. I never use this, but I'm pretty sure some people do, maybe. Okay, if you want to find a matrix to a really large power, it's a pain in the butt to multiply it by itself so many times. So you can use the little diagonalisation trick to do it. So if you raise that d to the power of q, it's like having that p minus 1 ap times by itself, q times. And then all the p and p minus 1s cancel out in the middle there, and you just get the A matrix raised to the power of q. Rearrange the p minus 1 and the p, and it's heaps easier to raise a diagonal matrix to the power of q than it is to raise a normal matrix. But we're not going to do that last example. There you go. Okay. What's next? All right, so the next thing we get to do is actually do things with eigenvalues and eigenvectors. So far we've been finding them, but what can you do with them? This is one thing that you can do with them. So I was going to show you the bridge movie on Monday, but you've already seen it too many times. I'll show you a different one next Monday. So one explanation of what was going on in that one that you'd seen, the Tacoma Narrows one, is that the wind was blowing at such a speed. It wasn't very fast, but the speed exactly matched the resonant frequency of the bridge. Okay, so what happens then is that you get a small oscillation, but it gets reinforced every time, and then the oscillations just get massive and it's smashed down. The same thing can happen when soldiers march across a bridge. So if they're all marching at the same time, and if it just so happens that their speed of marching matches the resonant frequency of the bridge, they can actually make the bridge fall down, and that's happened in the past too. So if you go to places where there's old bridges, near an army town or something, where troops used to march around, there'll be a sign on the bridge saying that troops must break step before they cross the bridge. So they can't march across the bridge, they've just got to all stroll across the bridge, so they don't crash it down. And I said this last week too, the eigenvalue that matters is the one with the smallest magnitude, because what we're interested in is 1 over lambda, and so the smallest lambda is going to give you the biggest 1 over lambda. Okay? All right, what else? None of you are old enough, I don't think, to know about this thing. But when you had an old-fashioned wireless and you would tune into the radio there, what you were doing was moving things across to make the resonant frequency of your wireless the same as the station that you wanted to catch the music from. Okay, so that's how radios used to work. When you're tuning instruments, this is how they work as well. Everything's got to match up to the same resonant frequency. The other one, which you guys are probably more familiar with, you know when you see a car going down the street and its stereo's up really loud and you can hear it shaking? You do that all the time? Yeah, okay. Right. So that's because the resonant frequency of your car is the same as what's coming out of your stereo. And so it makes these tiny oscillations which you wouldn't normally notice into these bigger ones and the whole thing shakes. So maybe change the resonant frequency of your car. I don't know how to do that, but anyway. That's what you can do. Okay. So when you see someone go down the street, you can nudge your friend and say, oh, I know that's eigenvalues. Okay. All right, the other place they come up, and this is a real one that you see as well, is in circuits. So if you have a circuit that's being driven by an alternating current, right, and if you have the frequency of that oscillation of the alternating current matches up with the natural frequency of the circuit's going to blow up. All right, so those electrical engineers here, pay attention for this reason. Okay, you can design stuff that will actually blow up. And somebody used to have a circuit, and I haven't got it, and that person's no longer here, but you could actually turn it on and it would blow up in class. Okay, but we don't have that, unfortunately. Yeah, but I think they just stitched it up again and used it again. I don't know. I don't think it like completely has a giant explosion, but anyway. Okay, so this is how the ones for an electric circuit work. If you have an electric circuit like this, let's pretend I've got these two loops. Okay, this shows my technical skills. I don't know how to draw on a computer, so I'll draw it by hand and stick it on. I've got these two loops here that's going on here. I've got some resistance here, I've got some capacitance here, and I've got some inductance here. Okay, and here I've got an alternating current, or even just a DC current if you like. I can write equations that will tell me what the current is doing in this circuit, and another equation that tells me what the current is doing in this circuit. Okay. Now the I1 and the I2 are the currents, and the current will vary with time. So I can write down like a rate of change equation that shows how the currents will vary in time. And the first one will depend on things like the inductance, because that's where the inductor is, and the resistor. But it will also depend on what the current is in the first circuit and the second circuit. And you can write down something similar for the second one, but that one's got the capacitance. Capacitor. That's got that in there as well, right? Now the thing to notice here is you want to know what the current is, right? You want to know the current in the first one and the current in the second one. So you've got differential equations to solve. The tricky part is that the differential equation depends on both of the other currents. And this differential equation depends on both of the other currents. Okay? So the question is then, we know lots about matrices now, because we've been working hard. We know lots about matrices. Can we write this in the form, like in matrix form, and then we can use all our stuff that we know about matrices to figure out what's going on? And the answer is yes. Okay. The things that we don't know is I1 and I2. So that's going to be our unknown vector. That's like our x1, x2, x3 from before. Here's our coefficient matrix. So I pluck out the coefficients of the I1 here and the I2 there. So here I've got minus R over L, and here I've got R over L. So that's what those are coming there. And in the second equation, I can write the coefficients in the second part. So one here and one there. Don't forget the L out the front. And then this E thing, the driving force, the battery, doesn't depend on the current. So that kind of stands alone like a little column vector. Okay? So I can rewrite this equation like I primed, and a prime is a derivative with respect to time. So I primed, so it's the derivative of each of these things, is equal to this coefficient matrix times by the column vector of the things I want to know about, plus this battery thing here. Okay? So now we've got it in matrix form, and all the important information is tied up in that A and the E, And so we can do things with those A and E's to figure out what's going on in the circuit. And then we can get rid of all this stuff and just put it back in at the end. All right, here's another problem which is actually identical. Here's my drawing skills. Okay, so we've got a little bucket of water, and in here we've got this mass tied onto the end of a spring, and we're jiggling it up and down. Okay, so the jiggling up and down is this F here. Jiggling up and down is this F here. This is the mass, so that gives it some inertia. This is a damping part, right? So that's going to be the effect of the water slowing the mass down. And this K thing here is how much energy the spring stores as it bounces up and down. Okay, so we can write this as a second order differential equation, and I'm just writing your computer project right now, and it's got equations like this in it. Okay, so bouncing spring stuff. If the F is equal to 0, then it's called homogeneous. Put all the interesting stuff on the left-hand side and it's homogeneous if there's a 0 left. What we can do, this is second order. These were two first orders. Because we're clever, we can turn one second order equation into two first order equations. I'm going to show you how to do that today. Okay, so now because I've got two first order equations, what I can do is I can write it in a matrix form. So the y1 and the y2 are the things I don't know about. The coefficient matrix in the first equation, I've got 0 y1s and 1 y2, so that's where the 0 and the 1 come in. And then these are the coefficients in the second equation, and then I've got this forcing term here. Okay? All right. Does anyone want to ask any questions so far? No? So the first thing we're going to talk about is if you have a bunch of first order equations, how do you write them in matrix form? That's the first thing we're going to talk about. So you can have any number of first order linear ODEs. They've got to be linear, just like the operations stuff. Then you can write it in matrix form, right? So I've got that equation there in bold, y prime. So the prime means derivative, differentiate with respect to time. And then you pluck out the coefficient matrix, and the coefficient matrix is just all these values in front of the things you don't know. So it's exactly the same as before, okay? All right. Oh, that's the other thing I have to say. When we're doing this part of the course, we're always going to have problems where f is equal to 0. Right in week 13, we're going to do some problems where f is not 0, okay? But for now, that's what we're going to do. All right. First example. Okay, write this system of equations in matrix form. So the thing to notice here is they're differential equations. So I've got the primes on the left-hand side, that's a derivative. And they're linear, so I don't have any x squareds or y cubes or sines of z's or anything like that. They're just linear. Okay? All right. So prime means d by dt. Let's just write that down first. All right, I can put this straight into vector form just by making this one column vector and this one column vector, even though it's pretty fat. So we'll do x primed, y primed, z primed. Okay. So far, so good. If we look at this right-hand side, remember when we did systems of linear equations and then we put them in matrix augmented form and did our row operations? This looks like the left-hand side of those equations, so we can separate the numbers and the x, y's and z's. Okay, and that's what we're going to do. So pick out the numbers. Okay, and here I've got an x, y and z vector, and here I've got an x prime, y prime, z prime vector. So we can make them a bit more the same by taking that derivative outside. Running out of space yet? Okay, so now I'm going to relabel that to be y primed is equal to ay. Okay, so y is my vector of unknowns. The left-hand side I've got the derivative, and the right-hand side I've got ay. Now you can't just do that, you have to say where y is equal to x, y and z, 3, 2, minus 10. There we go. Okay. And that's it. Is everyone happy with that? It's pretty straightforward. Okay, so the point of doing this is when you have the equations like this, they're all kind of separate. They're all kind of separate and you can't really isolate the important information. When you do this, all the important information is contained in here. Right, so this is what we can work with, and we know lots about matrices, so we can do stuff with that. Okay. What's next? Okay. Everyone done with that? I think. Yep. Okay. All right. Let's turn this so that you guys are on the same page as me. All right. Listen carefully. This is a little bit harder. If you have a linear equation that's of higher order, so a linear equation that's of higher order would be like this one here. This is a second order one, and it's linear because the y isn't squared or anything fancy. The first derivative's not squared, the second derivative's not got anything fancy either. Okay, these things are just linearly adding together. So any equation that's like this or higher order is called an nth order ODE. You can rewrite that as a system of n first order ODEs. Okay, so I did it on the other page. I changed that second order one into 2 first orders. You can do it with any order one. So a third order one would turn into 3 first order equations. Okay. On this page, it tells you how to do it, but it's probably easier just to do it. Yeah, I think we'll just do it because it's easier when you work your way through it than reading it. So we're going to do these 3 examples. Now, most students in the past have found this to be one of the harder things to do. So let's make sure that we get it done properly. Okay. All right, so first we're going to do a second order equation here. Now when you do this, let me just change this one for a minute. When you do this, I should have said this first. Okay, so we've got an nth order equation here. What you do is you introduce n new variables, and I'm going to write first order equations for each of these n new variables. Okay, so if you have a second order, keeping somebody awake, if you have a second order equation here, right, you want to introduce 2 new things here. Okay, so that's what we're going to do. And when you do it, you should write that down to remind yourself. So it's a second order. Okay, so we're going to need a y1 and a y2, and those are going to be our new variables, and we're going to have first order equations for them. Okay, so y1, when I introduce y1, I'm going to make that to be the same as y. And when I introduce y2, I'm going to make that to be the same as the first derivative of y. Okay, and now we concentrate on finding out what y1 and y2 are doing, and then right at the very end, we'll see what that means for y. Okay, what you do then is you differentiate both of these sides with respect to x, because that's what this problem is. So differentiate both sides with respect to x, and you get y1 primed is equal to y primed. That's good. Differentiate this one, and you get y2 primed is equal to y double primed. Okay, now I'm going to turn this one back for a moment, if I can. Okay, so y1 primed and y2 primed. Here. y1 primed and y2 primed, that's... Oh, fuck. Excuse me. Okay, this is why... Not very good. Okay, so I didn't even touch it. y1 primed and y2 primed. This is what we want on the left-hand side, right? So that's exactly what we've got on the left-hand side up there. On the right-hand side, though, we want something with y1s and y2s and no derivatives. Okay, so you can see up here, we've got something with y's, not y1 and y2, and they've got derivatives. Okay, that's not what we want. So we fix that up. We fix that up by saying, well, here's a y primed, and I know that y primed is equal to y2. Okay, and now I've got a thing there that's not a derivative, and it is a y1 or a y2. That's what I want. All right, this second derivative here, well, I can't do the same trick with that because it doesn't appear here. But what I can do, I could rearrange this, because here's a second derivative. So let's rearrange that. Y double primed, whoops, take 3y equals 0. 3y, take away 2y primed. Okay, so I can replace this one here with this stuff. Okay? Bless you. All right, so now I don't have a second derivative, but I do have a first derivative, and I have y's, and I don't want y's. I want y1 and y2. But here, I can look here, I've got a y, and here I've got a y, so I can replace that one with a y1. And this one here, I can replace it with a y2. And then I've got what I want on the right-hand side as well. So for the first equation, I want these parts. And for the second equation, I want these parts here. Okay, so let's just write that down. y1 primed is equal to y2. y2 primed is equal to 3y1 take 2y2. Okay, now if we're going to write that in matrix form, the left-hand side looks good. The left-hand side looks good. Just wondering how many steps to put in here. Okay, so I could do y1, y2 and take the prime to the outside, and that would be like the left-hand side. The right-hand side would be like, well, I've got 0 y1s and I've got 1 y2, 3 of those and minus 2 of those, y1, y2. Okay, so now I can just write y primed equals ay, where y is equal to y1, y2 and a 3 minus 2. So this is the thing that you're looking for. You've got these two, well, a vector and a matrix here. You've got a little equation that says how they're related. All the information about the whole problem is tied up in here. Well, together with that, but mostly in here. Okay, and we can do what we like with that. Does anyone want to ask any questions? We're going to do this a couple of times. No? Okay. All right, the next one. Okay, so this is a third order equation, so that means we're going to need 3 new variables, and I strongly advise you to write that down. Okay, so this time we need 3 new variables. Right, so now you have to introduce them all. You choose y to be the first one, then the first derivative, and then the second derivative. We're going off the page. Yep. Thank you. Okay, then you differentiate. Differentiate with respect to t, because this equation is a derivative with respect to t. Then you get y1 primed okay, so I just differentiated all three of those little things with respect to t on both sides. And now the left-hand side looks how I want it, but the right-hand side doesn't. So I can have to find a way to replace all these things, right? So the first derivative, I can find that here. That's going to be y2. The second derivative, I can find that here as well. And the third derivative isn't here, but the last one is what you always get from here. Okay? Oh, look at me. All right, these should all be x's. Sorry. You know what I'm going to do? Don't do that. Let's change these to y's. There we go. That's easier. Okay. Now, if I rearrange this one, I can get y, 1, 2, 3, 7, minus. Oh, now I've completely lost it. All right, let's see if I can do better than this. All right, so the third derivative is here, and I get that from the equation, 7y double primed plus 8y. And this is still not what I want, but I can replace all these things with my new variables that I listed here. Okay, so the second derivative is going to be what? y3 minus 14 y2. Let's keep that to be a y. And the zero derivatives should be y1. Okay, so now we've done the hard work. So this is the first equation that we want. This is the second one that we want. And this the third one that we want. Okay, so write them all out and then we'll write them in matrix form.
Why is that y3 also equal to 0?
Oh, shouldn't be equal to 0. I completely stuffed that up, didn't I? Yeah, no, it's not equal to 0, that's right. Okay, here's a little trick that's easy to make a mistake. See how when I did this, they didn't turn up in the right order? When I write them down here, I'm going to write them in the correct order, because if I get them in the wrong order in my matrix, I'm going to be stuffed. Okay, so get them in the right order here. 8y1. Okay, so now we can write them in matrix form, and I'm going to go straight to this part here. Okay, so it's going to be on the left-hand side, I've got all the derivatives, and a coefficient matrix times by the things I don't know. The y column thingo is going to be 1, y1, y2, y3. And the coefficient matrix, you just got to be careful where you put your zeros. Okay? So here in this one, I've got 0 y1s, I've got 1 y2 and 0 y3s. Okay? This one I've got 0 y1s, 0 y2s and 1 y3. And here's where you had to get it in the right order. 8 minus 14 and 7. Okay. Does anyone want to ask any questions about that? Sorry. Yeah, it gets a bit hazy at the bottom there, doesn't it? The light, oh, this one. Oh, good. There we go. Oh, wait. Maybe that's as good as it gets. See what he's done? Okay. All right. Then we have a couple of more minutes and then we'll have a break. We're going to do a third one. Who's chitter-chatting now? Lots of people. All right. We're going to do the third one. The reason I'm harping on about this is because if there is a question like this in an assignment or exam or somewhere else, this is the first step of the problem. If you can't get the first step of the problem, which is going to be like 20-something marks to do one of these problems, you kind of can't get any of the rest. Okay, so make sure you know how to do this part. All right, so third order equation. So that means we're going to need to introduce 3 new variables. I'm going to rearrange this too, hopefully properly. 3y double primed minus 4y. Okay, so I've got that ready to go when we need it. All right, so introduce these thingos here. Y1 is just going to be y. And that's where I'm going to stop because I said I need 3 and that's 3. It's tempting to write another one because it's a third derivative and we've got a third derivative. But that's all we need because that's what we said at the start, so don't keep going. Okay, differentiate both sides and what do we get? Y1 primed. One, 2, 3. Okay, so the left-hand sides look good, but the right-hand sides don't. We don't want derivatives and we don't want y's. We just want these new things. So y primed I can replace with a y2. Y double primed I can replace with a y3. This one, I'm going to use the ODE. Then I'm going to use this stuff. Okay. So now the right-hand sides look good. Okay, so we've got the first one here, the second one here, and the third one is down there. Do I stuff something up again? That's okay. Yep. Thank you. Okay. Minus 4. Okay, so now we can write it in matrix form. So the vector that we're going to introduce is going to be the y1 and the y2 and the y3. On the left-hand side, we've got the derivative of all those things. You can take that outside the vector. And then the coefficient matrix times the things that we don't know. So So 0 y1s, 1 y2, 0 y3s. And this is the part that we want. Does anyone have any questions?
Will the top two resolutions?
Yeah, they will when you do a 3 by 3. Yep. Yep. Okay, so the thing we're going to do next is we're going to learn how to solve this equation here now that we know this coefficient matrix. Okay, and once we solve this, we know what y1 and y2 and y3 look like. The thing we've got to think about then is what we really want to know is y. We don't care about any of these things. We want to know about y. So you go back to here and say, well, y is actually y1. So this is the one that we're going to care about to find our answer to this problem. But in the process, we have to find these ones because they're all linked together. Okay, so that's what we're going to do next after the break. So let's have an early break because there's no point starting the next bit in 5 minutes. But we might come back 5 minutes early, okay? So 5 past. Oh, sorry. Were you finished? You sure? Okay.
I skimmed through the assignment and the first one was, yeah, the new one says show that these two eigenvectors are, eigenvectors are. Can you just do this? That's what you want.
And I'll tell you what the so the other way to show it is to find them.
Okay.
Right? You know where at the end of the question it says what we answer that bit's only where we
Okay.
so it's not very much work.
Okay.
That's not very much work, right?
Yeah. So do that, and then yeah. Okay. And then for the third one, we have to actually do the process of finding something.
Yeah, so the third one we should be able to get the eigenvalue pretty easily.
Oh, that way.
Yeah. But the vector you've got to
Okay. Thanks.
Quick one here. I can't work this one out.
how to get from there to there.
Yeah.
Okay.
Well, I sort of get most of it, but why don't we have a negative on C? Because you take those over to the other side, right? So you get the negatives.
No, I had this part in the notes for
And that's so weird.
Yeah, no, it should be
because I'm actually terrible at details, so that's so weird.
Alright, I'm going to write that right now.
Now the other question is more of a generic one. So
This one's right though, right? Yes.
yeah, that one's oh, no. I'm worried that if you had it in that line, I'm missing something.
No, that's right.
So why are we heading to the y prime here? Is it because we need something to be able to work with, or is the y prime actually a goal?
Do you mean why do we want to write this vector?
Why specifically a y prime? Is it because all of our equations that we're going to end up trying to solve are derivatives?
So we're going to now look at systems of first order ODEs.
Yeah.
So systems of first order ODEs will always look like first
We're
order
going to always
linear
end up with
ODEs. Will
derivatives
always
that we're
look
trying
like
to
this.
solve.
So they're first order, so they've always got a first derivative,
Yep.
which is what that is. So it's a vector. So we've always got a first derivative, and they're linear, so it means you don't have any squares or anything fancy on this side. and you have to solve them all together at once because they all depend on each other and you can't so always is going to be a first derivative on this side.
Yeah.
You can actually get a fourth order equation and turn it into two second orders.
Okay.
And if you want to
So then
so
you
you
wait
just
till
keep
it is.
going, yeah, that's right. So, but in this course we'll be looking for the first derivative on the left hand side.
Yeah, cool. Okay. Yeah, so it's a function of the equation you try to solve.
That's right.
Yeah, cool. Awesome. Thank you.
No worries.
If the eigenvalue of a 3x3 matrix, you obviously have three eigenvalues. If one of them is a 0, and then you have that every single eigenvector that you're going to have is going to be multiplied by 0. So
Every single eigenvector that corresponds to that.
yeah. So then does that mean that that vector is not 0? It could be any. That could be any.
Yeah, I understand what you're saying. It still has to have a direction in it. It sounds funny. But if you're doing really complicated special directions, when you're doing it one here, when you're doing it numerically, so it's still going to be a direction, but what you have is just a special direction. The special thing about this direction is when you do the transformation, it goes to net 0. But if I take this vector here, it's not going to go to 0, so it doesn't correspond to that eigenvalue.
So you
So only the ones above
So you could have an eigenvector, an eigenvalue that's 0, and then check your answer and you just get 0. And it still is, that's still an eigenvalue of eigenvector. If you take out the 0, you're going to...
yeah, so it's still an eigenvalue, and you found the wrong eigenvector, but you didn't know it.
Yeah, it is, yeah.
Oh no, wait a minute. No, that's not quite true because if you took that A matrix and times it by a vector,
Yeah.
and if you had the wrong vector here, you're not going to get 0.
Oh no, but if you do get 0, then it is the right value.
Yeah.
Oh, cool.
Yeah, so you can check. Yeah, that's right.
Yeah.
Okay,
Yeah, that's more what I meant.
yeah. Yeah. No, there wasn't 5, all the 5 was 2. I haven't seen 5 as 4 one.
So pretend it's touches H. Yeah, so then if you cut out the square, the perimeter's still going to be 4, right? So just keep cutting out the squares. Which means eventually on the outside of the square, so 8 is 4. And that's the difference here. So with this one as well, then it's different.
Yeah, there's lots of problems.
Job sound. So is there actually supposed to be a question for this, or is this just like
Actually, this one is not. Can you do it in terms of limit? I think you can probably do it in terms of limits. Yeah, the trouble is that if you take the limit as n goes to I think that's the problem with this one. If you take the limit as n goes to infinity, we've got an n in the problem. If I have to
question?
yes?
Remember on Monday, where we did determinant, or we found the eigenvectors on the right side.
Monday. Yeah.
And then when we had 2 zeros in the matrix, to do the determinant, if we used the row with the 2 zeros, we always ended up with a linear algebraic factor. Is that always the case? So if you have
There's 2 zeros.
2 zeros, you always end up, you don't actually have to factorize yourself, it's always a linear algebraic.
Okay, so what you require then is we have a matrix. I think why we have should do is, I mean, you should find the determinant in the easiest way you can, right? Because the easiest way is going to be the way that you see that is there. And as soon as you found the determinant, you can see, is there anything that's making my life easier already? So that's the best thing, because sometimes you might have a case where something like this, right, and you'll have a linear factor times by some complicated part, which is the determinant of this part. And you have a number here times by something here that's got maths in it. It may turn out that this factor here is repeated in here. And then you've got it here and you can take it out of there. So then it's another case where you've got linear and then you've got to only deal with this and the leftovers in here. So sometimes it will come up without that happening. So the best idea is to do the determinant the easiest way, and then as soon as you've written that down, you can see, can I make my life easier? And most of the time, to be honest, if I put this in the exam, most of the time I try and do that, and some people see it. So I'm trying to make your life easier, right? But not everybody. But so often in the exam that's what happens, but not always. I've done it yet. But it's also hard to write problems that do that, right? It's really hard to try and make sure it's going to have either ways that are real numbers, not complex, not fractions, and then the argument you can work out nicely. That's right. And that's why I'm doing it so easily. Because in that case, let's get cracking, shall we? Okay, so there was no question here, but the thing that I put up here says 2 equals 1, and clearly that's not right, or the whole system comes crashing down. Can anyone tell me what's wrong with this description, apart from 2 equals 1's not right?
The matrix had a glitch.
The matrix had a glitch, yeah, maybe. Does anyone know?
It's just the first triangle that is split into different segments, so on that segment there, you split it into 4.
Yep. But you've still got... Yep. But nothing's wrong with that. You've still got 2, you just cut it in half and made it a different shape each time. Does anyone know? I'll tell you what happens. Just because you've got infinite amount of these triangles and they're getting infinitely small doesn't mean they still... So these triangles are infinitely small, so you think maybe they don't have any extra length when you go up and down, but you've got an infinite number of them. So when you have an infinite number of tiny small things, you end up with more than what you think. I guess that's the answer. And here's the proper answer. So if you multiply the length of each segment, after you've done this n times, the length of each segment will be 1 over 2 to the power of n minus 1. So the first time you do it, the length of this will be 1/2. The next time it'll be 1/4. So that's what this part is. And every time you do it, you end up with 2 n triangles. So the first time you do it, you get 2, the next time you get 4, the next time you get 8. When you multiply these things together, the n parts cancel out. You just get 2 to the minus 1 on the bottom line. It's equal to 2. So actually 2 is equal to 2. So they are tiny little triangles. There's just heaps and heaps of them. All right. There we go. How exciting. Okay. All right. What are we going to do now? So Let me go back to here. So in this part of the course, we're only going to look when this f thing is 0, right? We're going to have homogeneous equations, they're called. Now have a look at this. What we've got here is the derivative of the function, derivative of something, pardon me, the derivative of something looks exactly the same as itself, but it's times by a bunch of coefficients, a bunch of constants in the front. What function do you know when you take its derivative, you get the same thing back again, but maybe a constant? E, who said that first? You can have a lolly. Exponential. If you take the derivative of an exponential, okay, you're going to get that exponential back again. Okay. You can also see that if you solve this equation, so you guys will have done this, someone asked me to use that smartboard, but I still can't figure it out. It's on my list of jobs to do, I haven't forgotten. Let's do this problem here. This y is not a vector, this is just a normal function. So this is what you did in MME1. Okay, and if I can see it like this, I can see that it's separable. I can rearrange this so that all the y's are on one side and all the t's are on the other. To do that, I get something like this. Okay, now once you've separated all the y's on one side and all the t's on the other side, you can integrate both sides. I'm going to integrate this one with respect to y, and I'm going to integrate this one with respect to t, and then I get something that looks like this, plus a constant, I'm going to call it c tilde. Okay, now if I know my log laws, which I do, and hopefully you do as well, I can rearrange this to be e to the kt, so raise each side to the power of, raise each side to an exponential, no that's not right, plus c tilde, that's not right, and that's the same as having a constant out the front, e to the kt. Okay, so this is where the exponential thing comes from. You can think of it as by solving this differential equation, or you can think of it by saying when you differentiate the exponential you get the same thing back again, but maybe a constant's in the way. Okay, so this is what happens when you've just got one little function here. The question we want to answer is what happens when you have a column vector here of derivatives, a column vector here of the things that we don't know, and a matrix here. Okay. So the first idea is let's try something that looks kind of the same. Okay, so here I've got a vector. Okay, here I've got an A and here I've got a K. So let's, instead of putting the K here, let's put a matrix A here. So that's what I've done here, matrix A. And then in front of here, instead of having a constant, just one constant, I'm going to have a column vector of constants. And I have to write the exponential first and the C second, because when you're dealing with matrices and vectors, you have to make sure the order is right to get the right size for your multiplication. So that's why these are kind of backwards. Okay. If you do this thing here, this is called a matrix exponential. So you've got an exponential to the power of a matrix here. You can do that in a bit of a convoluted way by using this thing here. This is a Taylor series. Have you guys seen Taylor series before? No? So what it basically says is I can, instead of having this function, and it can be any function, in this case it's an exponential, I can approximate it by a sum of different things and not involve that function at all. Okay? So you can see here I've got a function of this thing here, and I can approximate it by this giant sum, and I don't have any exponential terms left here at all. Okay? And that's probably about as much as I'm going to say about that. Okay, it's called a Taylor series. This, or you can do a Maclaurin series as well, but this one's a Taylor series. Okay. Anyway, but if you differentiate it, what you get is exactly what you would expect. Okay, this A comes down the front, so there's our extra constant, and you get the same thing back. Okay. So then the question is this thing a solution? Well, let's check. So the derivative on the left-hand side looks like this. Right, that's the derivative that goes in there. Now, the right-hand side, with a C in it, and so you can see that it just matches up, and yes, it's right, okay? But the question is, when you have a matrix exponential, it's actually quite, I know I've just written that they're like a Taylor series, but it's quite a thing to get a head around, and we're not going to do that here. If you do a linear algebra course, like a whole course, not a half course, it's in there. Okay. Here's a second choice. Why don't we put, I'm kind of giving it away here, why don't we try having the vector of things that we don't know is equal to a column vector here of constants times by an exponential to just a constant power times by t. Okay, don't forget these are functions now, so they're functions of time. They're functions, whoops, I'm going the wrong way. They're functions of time because of this kind of thing, right? We've got derivatives with respect to time. So let's try that we're going to have a vector times by an exponential lambda t. Okay? All right. If we substitute that in, the derivative on the left-hand side, the derivative would just, well, this is constant, so that stays. Take the derivative with respect to t and the lambda comes down. So this is what we get on the left-hand side. The right-hand side will be equal to a multiplied by this thing here. So that's what we get there. Now I can cancel out the exponentials. You have to be careful cancelling things out. If it can ever be 0 and you cancel it out, you've got dramas. But the exponential of anything can't never be 0, right? The graph goes like this, never reaches 0. So we can cancel that out and not worry about it, and then we get this. Tell me what this looks like. Pardon? Eigenvector. Who said that? Yeah, eigenvector. So x is going to be our eigenvector and lambda is going to be our eigenvalue. All right, everybody watch out. Oh, look at me. Okay, so we can rearrange this. I'm not going to do it here. So x is going to be our eigenvector and lambda is going to be our eigenvalue of our matrix A, and we know how to do that stuff. So that's what we're going to do. So you would take this thing here. I'm just going to do that on the board as well. So if you had lambda x equals ax, okay, so if you rearrange it, it looks exactly like the stuff we've been doing. Okay, so lambda is the eigenvalue and x is the eigenvector. Okay, so this is what you do. If you have a 2 by 2 system of equations, okay, this is exactly what you do. If you've got a 2 by 2 system, you're going to have 2 eigenvalues and 2 eigenvectors, okay? Now, for now we're going to talk about what happens if the eigenvalues are distinct, okay? We're going to come back to what happens when they're equal later on. But if these are distinct, then you're going to get 2 eigenvectors, and not only that, they're both going to be linearly independent. Okay, we talked about that the other day. Now, because we've got 2 eigenvalues and 2 eigenvectors, we can make 2 different solutions, right? This is what our solution is going to look like. We can do this thing twice, once with lambda 1 and x1, and once with lambda 2 and x2. Okay, so that's what we do. Here's one solution. And I've put a little 1 in brackets here because I'm calling that the first solution. The second solution is going to be with the second eigenvalue and the second eigenvector. Okay. All right. So this, what I've got here, is exactly the same as this, but it's just expanded. Okay. So this first solution, don't forget this is a vector, and inside this vector is y1 and y2, and they're both functions of time, right? Think about the current in an electric circuit, how much current there is at a certain time. And then here on the right-hand side, we've got this first eigenvector here, multiplied by e to the lambda 1t, okay? And the second solution, you can do exactly the same thing. So now I've got 2 solutions. Now, there's a big theorem that says that if you can get linearly independent solutions to an ODE, the most general solution you can have will be a linear combination of those things. Okay, we're going to talk more about that when we do calculus. So if you have linearly independent solutions to a differential equation, the most general solution will be the sum of those. Okay, actually a linear combination of those. So here's one solution, here's another solution, We're going to add them together to get the most general solution. And because it's a linear combination, you're allowed to multiply them by constants. And this will be the answer to the problem. Okay? Everybody copies that one. It's amazing. Okay. So don't forget though, in here is a vector. So you've got a y1 and a y2 in here. So you can pick out the solution to y1 by looking at the first row of all of this. So the first row is going to have a C1. It's going to have the top entry from here, and then it's going to have this. And a C2 and the top entry from here, and then it's going to have this. Okay? And the y2 will be the bottom entries. Okay? All right. Does anybody want to ask any questions? No? All right. We're going to do a little example. This one. Okay, what we're going to do here is show that this solution is a solution to the differential equation. Let me just switch this back for a minute. Okay, so basically we know this one's going to be a solution and we know this one's going to be a solution because that's what we did just here, right? The point of this thing here is I'm going to show that this linear combination of the two is still going to be a solution to the differential equation, okay? That's what we're going to do. Okay. All right. I have this thing about proofs. When you do a proof, you have to start with the left-hand side and work your way until you get the right-hand side. Or you can stick everything on the one side and work your way until you get to a 0. Okay? Something that you cannot do is put the left-hand side equals the right-hand side and rearrange things until you get 0 equals 0. Don't do that. If you do that, you're assuming that it's true when you start. Okay? Don't do that. You have to start with one and finish with the other, or stick it all on one side until you get to 0. I'll tell you the difference with what I did here. Here, I put down the left-hand side is equal to the right-hand side. Here, I wasn't proving it. Here, I was trying it and testing it. I put it in, and it tells me, yes, it's true, only if these things are eigenvectors and this thing is an eigenvalue. Okay? Oh, have I? Sorry. Pointing and no one can see. The difference with what I did here is I was trying it, right? I was saying, let's try this one, stick it into the equation, left-hand side equals right-hand side, and now I've got this, and I can say, this is only true if these are eigenvectors and this is an eigenvalue. Okay, so this isn't a proof. This is like a try and see if this is going to work. All right, now we're going to do a proof, this one. So you have to start with one side and finish with the other. Am I doing the right thing now? Okay. What time is it? 23. Okay, so y prime take away a y equals... Alright, so we want the derivative with respect to time of this thing. Don't forget the c's are constant, the x's are vectors full of constants, so that's a constant. So t is here's the only place where t appears, right? So I get c1, I'm going to stick all the constants out the front. Lambda 1, x1, e to the lambda 1t. And the derivative of this one, lambda 2, x2, t. Okay, so that's the derivative, and now I'm going to do minus a times by this thing here. If I do a times by this one, the constant can come out the front, that's okay. But I better not change the order of the matrix and the vector. So the matrix has got to come next. 1, minus did I stuff something up? I think not. Okay, all right, but this is an eigenvector and this is an eigenvalue, so we know that A times x1 is going to be equal to lambda 1 times x1. And A times by x2 is equal to lambda 2 x2. Whoops. I primed minus AY equals minus C1, and I'm replacing AX1 with lambda 1x1 minus C2, and A times by x2 gets replaced by this one here. There we go. Okay, and all of these cancel out and you get 0. So that means that y equals C1 x1 e Okay, so we have these, for 2 by 2, you have these two eigenvalues and eigenvectors, so you can make a solution out of each one, and the most general solution is going to be the linear combination of those two things. Okay, does anybody have any questions?
Is it going to be an example?
This proof? Or any proof? Something like this could be like a show that, but it won't be something you haven't seen before. So it'd be something like this that we've already seen, if there's something like that. Okay, all right. Is everybody done? Yes? Okay, for a minute we just need to talk about the constants of integration. So these little c's here, when we add these two solutions, so here's one solution and here's another solution, we make a linear combination of them. That means we're allowed to multiply them by a constant. Now we don't know what these two constants are, right? But this is a solution to a differential equation, which basically means we've done some integrating here. Okay, when we did integrating here, we added a constant of integration. Okay, and these constants of integration here are almost the same kind of thing. Okay, this was one first order equation. For one first order equation, you're going to get one extra constant. For two first order equations, you're going to get two constants, and this is where they come up. Okay, so these are the constants of integration. And remember, when you've got those constants of integration, you can find them, or this one here, by using some initial conditions, right? If I tell you what's going on when t is equal to 0, you can find out what the value of c is, okay? So that's what this says. When we take a linear combination of two linearly independent solutions, we introduce two arbitrary constants, and they're the constants of integration. Okay, each differential equation has got lots of solutions, a different solution for each value of the constant, and each value of the constant corresponds to one set of initial conditions, okay? So here we've got two equations. This was a system of two first order ODEs, what we've been talking about. If you've got three first order ODEs, you're going to get three constants of integration. There'll be three eigenvalues, three eigenvectors, you add 3 together and you'll get 3c's, right? So the more you have the same number of constants of integration as you do for differential equations. It's the same as if this was one second order equation, you'd end up with 2 constants of integration. Okay? All right. The other note, the same solution technique can be applied to larger systems. Everything works exactly the same, you've just got more work to do. Okay. Let's do this one. So now we're actually finding solutions to differential equations. Okay, so don't forget that these types of equations, you can write down these types of equations to show what's going on in an electric circuit. You can do it for showing what's going on with bridges. You can do it for buildings. You can do it for, if you have a mine shaft and you're worried about earthquakes, you can look at how earthquakes, and you'll get these kind of equations as well. They'll just be bigger and more complicated. By the way, with an earthquake, when you have an earthquake, there are 2 different kinds of waves. There's the waves that do this, and then there's a wave that does this as well. And these ones are worse than the ones that do this. There you go. And it depends actually if this kind of thing is going on in this direction of the shaft, or if the shaft is this way and it's going that way. All right, let's not talk anymore about that. Oh dear. Okay, let's do this one. Getting myself into trouble. All right. Okay, so we're going to write it in matrix form. So here's our little thing in matrix form. But don't forget, you have to say what these things are. Oh, here's another thing. I'm going to start getting lazy, and I'm going to use capital letters for my matrices instead of putting a squiggle underneath. So I'm going to leave these squiggles off and have capitals for matrices, for vectors soon. Oh wait, I should say something else here. Okay, so this is a column vector, and each of these things are functions of time. Okay? So y1 and y2 are changing with time, and that's why we can find their derivative. And A is going to be equal to okay. All right, so all the information that we need about the problem is hiding in that A. Okay. Okay, so the procedure is find the eigenvalues, find the eigenvectors, construct the solutions, 2 of them in this case, add them together, and then we'll be able to see what the answer is. Okay? This one's going to be easy because we already did this matrix before. Woohoo! Okay. So you find the eigenvalues, don't forget, by doing A minus lambda I is 0. Okay, so we did this example ages ago. I can't remember which one it was. 43. So x1 was 3 and x2 was 1 and minus 2. Okay, so we already did the hard work for this problem. Normally this is quite a bit of work, right? We can skip over that. Okay, so for each eigenvalue and eigenvector pair, we can write down a solution. Now this is the first example we're doing, so I'm going to harp on about it a bit and write more than you normally would, but that's just the way it is. All right. So the first solution is going to be x1 times e to the lambda 1t. Okay, and that looks like 3, 4, e to the 7t. Okay, so that's the first solution that we've got. Now, because this is the first time we're doing it, I'm going to harp on about this a bit. Y1, remember Y1 was the first entry here in Y? So I can get what Y1 is by taking out the first part of this. So that's going to be 3e to the 7t. Okay, and Y2 comes from the bottom part. Okay, so this is a solution for Y1 and this is a solution for Y2. Alright, so that's the first solution there. The second solution, that's going to come from this second eigenvalue eigenvector pair. So Y2 is minus 3t. Okay, so we can get out the first part. Oh, I'm going to put little ones on these so we can see where they're coming from. So this one is going to be just 1 times by e to the minus 3t. And y2, the second one, is going to be minus 2e to the minus 3t. Going into the darkness. Okay, so this part here is the second solution, okay? So we've got these two solutions now. So the most general solution is going to be a linear combination of these two. The most general solution will be, bless you. So that's the most general solution there. So this is fine as an answer. And another way to write the answer would be to write out individually the y1 and the y2. So y1 of t Okay, so that's fine as a solution as well. Okay, so you can leave it in vector form or you can write them out individually. And sometimes, but I'll tell you when we do more of these questions, sometimes you'll really want to pick out one or the other. Okay, but we'll see that as we go along. Okay, does anyone want to ask any questions about that? No? That's all I wanted to do today. We worked hard. So you guys are free to